Hello and welcome to note quiz number 9, which is our second part of our discussion about polynomial functions. In the previous note quiz, we talked about graphing them. Our main focus here is going to be looking at finding the zeros or the roots of these polynomial functions. So what we're going to do first is review some ideas from before. The first of such ideas is long division. And with long division, the idea is to do this like a regular division problem that you would with numbers, but instead we're going to look at dividing polynomials. So the first thing you want to do is write it as a classical division problem as x minus 3 going into 2x cubed minus 7x squared plus a 0x as a placeholder minus 31. And now we're going to ask yourself, what would I multiply x by to get 2x cubed? And the answer is, of course, you would multiply by a 2 and an x squared. We now multiply that 2x squared times the x minus 3 and put the result down below. So when we multiply, we're going to get 2x to the third power minus 6x squared. Now we're going to subtract, and remember that means changing the sign and adding it up. So that's now a negative, that's now a positive. You'll notice the first terms always cancel out. And remember to always bring down the term behind it. Now we're going to repeat the process. So we're going to ask ourselves, x times what makes negative x squared? And that is going to be a minus x. We'll do that in blue up here. Put the result down below. Actually, let's keep that in black because we'll stay consistent with what we've been doing. So keeping that black, it's going to be minus x. Multiplying, get negative x squared plus 3x. Remember again, we changed the sign, so that's now a plus. And this sign is going to be a negative, or a subtraction, a minus. Combining like terms, we get minus 3x. Let's put that down here in blue. And we bring down our minus 31 from our division problem. And we repeat the process one more time. X times what makes negative 3x? Well, that's a minus 3. So minus 3 goes here. Multiply. Negative 3x plus 9. We now change the signs and add them up. And that's going to give us a negative 40. So our quotient, which is denoted as q of x, is the number of times that we divided in. And our remainder, r of x, is what we get from the remainder of the problem, of the division. So now when we write our final answer, the idea is that we actually have our quotient as the freestanding part of this, which was, again, 2x squared minus x minus 3, plus now our remainder, which is negative 40, over our divisor, which was x minus 3. And it should be noted here that if you were to actually add together this quotient and that remainder over x minus 3, it take you back to the original division problem, which is 2x cubed minus 7x squared minus 31 divided by x minus 3. So again, we would simplify down to this here if we added together those two things. All right, so now let's move on to some more calculations, and we'll talk about a different kind of division. We're now going to talk about what is called synthetic division, and you will notice that it is a lot more efficient to write than long division. First thing we do is we always take the opposite of what is behind the x. So we're going to take a 3, a positive 3, and write it in front of a partial rectangle. we now take the coefficients from the polynomial that we are dividing into. So we've got a leading coefficient of 2, followed by a -7. We have to use a 0 for any missing terms, and a -31. The process now works in this way. We bring down the 2, and we multiply the 3 times the 2 and get 6, and put the result below the -7. We now add up those two numbers and get -1, and repeat the process through the rest of the numbers. So 3 times -1 is now -3. Add them up. We then multiply 3 times -3 and get -9. And would you look at that? We get the same remainder of -40. And it should be noted here that the powers decrease by 1. So this is now the coefficient on x squared, the coefficient on x, and the constant coefficient. So therefore, our quotient, we know, is going to be 2x squared minus x minus 3 plus a remainder of -40 over x minus 3, which is exactly what we had before for our long division. So again, synthetic division is a very powerful shortcut. The one thing to be aware of here, which is extremely important, is you can only do this synthetic division when you're dividing by x to the first power. If there's a higher power of x, then synthetic division does not apply, and you have to use long division to make that happen. All right, so let's move on to another practice problem. Let's go through and do synthetic division again. Again, we always take the opposite of what we're dividing by. So in this case, we're going to use a -1 in front of our division. And you'll notice that we are missing the third degree term. So we have a leading degree of fourth power. Leading coefficient is 3. There's no x cubed, so put a 0 there. There's a -5 times x squared, then a 7, and then a -4. And we just repeat the process we did before. We bring down the first number and multiply. -1 times 3 is a -3. Add them up. Multiply -1 times -3 and get +3. Add them up and get -2. -1 times -2 is 2. 7 plus 2 is 9. We get a -1 times 9, making -9, and a remainder of -13. So our quotient now is going to start with x to the third power and count our way down. So we're going to have a quotient of 3x cubed minus 3x squared minus 2x plus 9 plus a remainder of -13 over x plus 1. And again, we could add this together and get the same thing as our original division problem. All right, let's move on to the last problem on this page, which again is another division problem. Since they're similar, maybe there'll be something a little different with the outcome. Once again, we're dividing by x plus 1, which means we're going to use -1 out front. You'll notice that we are not missing any terms. So we can just write down the coefficients as they appear. 1, 2, 1, -2, and -2. And now we can go through our synthetic division process. We bring down our 1. -1 times 1 is -1. Add up 2 and -1 to get 1. -1 times 1 is -1. Add them to get 0. -1 times 0 is 0. -2 plus 0 is -2. And then finally, -2 times -1 is a 2. Add them up and get a remainder of 0. We're seeing a lot of this coming up in this note quiz. Once again, the powers are decreasing, so our quotient is exactly 1x to the fourth, which we'll just write as x to the fourth, plus an x cubed, not x to the fourth, my apologies, that's x cubed. Remember, it's always 1 power less. Maybe I should write that little x cubed there. All right. So again, that's going to be a 1x cubed, or just simply x cubed, plus a 1x squared, no x's, minus 2. And again, that's our quotient, and there is no remainder. What this really means, and what we're doing a lot more of in a few minutes here, is saying that x to the fourth power plus 2x cubed plus x squared minus 2x minus 2 can be rewritten as x plus 1 times x cubed plus x squared minus 2. And if we were to multiply out this factored polynomial, we'd get back to the original division problem. So that's going to be our strategy moving forward. The goal is to take fourth degree polynomials or higher and reduce them down by 1, and then continuously reduce down that part till we get down to a quadratic that we can solve by factoring or the quadratic formula. Before moving on to that next page, I also wanted to make a comment here about our division problem. You will notice that if I was to substitute a -1 into the right-hand side, I would get 0. And because these two things are equal, these two expressions, therefore I would get 0 if I plugged it into the left-hand side as well. So it turns out that -1 is going to give me my answer if I was to do synthetic division. And that's actually referred to as the remainder theorem. So we'll talk about that next. The remainder theorem says the following. It says that if I was to go through and do synthetic division, the remainder that I get would be the same thing as just evaluating the polynomial function at that number. So what we want to do here is apply it to these two problems. So for starters, because they're giving me the value of c right away, I don't have to change the sign. If it was x minus -2 or x plus 2, then I'd have to change the sign. So what I'm doing here is I'm going to take my -2, and then I'm going to synthetically divide it into that polynomial. So -2, not sure why that's so tiny there. Maybe I'm over-zoomed a little bit. All right, so for our synthetic division, we're going to have a -2, and again, that's in front of 4, 10, -5, 7, and 50. So once again, we bring down the 4. -2 times 4 is -8. 10 plus -8 is 2. 2 times -2 is -4. -5 plus -4 is -9. -2 times 9 is going to be 18. 7 plus 18 is 25. -2 times 25 is -50. Add those up and get a remainder of 0. So that means that we have no remainder at all. And more importantly, it says that if I was to calculate f of -2, I would get the answer 0 from evaluating that function. So we do have a 0 for this polynomial for -2. Now let's repeat the process for 5. I'll give you a little warning here. The numbers are going to grow very quickly large. So let's go through, and you might want to have a little calculator out while you do this problem. We're going to take our 4, our 10, our -5, 7, and 50, and repeat the process. Bringing down the 4 and multiplying, we get 20. 10 plus 20 is 30. 5 times 30 is 150. Add that to -5 and get 145. 5 times 145 is 725. Add that to 7 and get 732. And then 5 times 732 is 3,660. Add them up and get 3,710. I warned you, numbers get big. So that remainder is nowhere near 0. So 5 is not a 0 of the polynomial. And again, to reiterate what we said earlier, if you were to calculate f of 5, you would get 3,710 from that calculation. All right, now let's move on to the main strategy here, or the main goal of this note quiz is going to be breaking down polynomials and getting their zeros. So for this first problem here, it's kind of a transition problem because they're giving us a hint and then they want us to completely factor the polynomial. So just like before, we're going to use synthetic division. We're going to put our 1/2 and divide that into 6, 19, 1, and negative 6. Now in this case, we are expecting to get 0 for a remainder because they're telling us from the start that 1/2 is a 0. But let's kind of go through and do the division to kind of show that as well. Plus, we're going to need the result from the division to do the rest of the problem. So bringing down my 6, multiplying by half, a half of 6 is 3. 19 plus 3 is 22. Half of 22 is 11. 11 plus 1 is 12. Half of 12 is 6. Add them up and get a remainder of 0. Again, it's not a surprise here because we expected a remainder of 0 because we were given the fact it was a 0. All right, so now remember again that the powers count down. So far we've got the following. We've got 6x cubed plus 19x squared plus x minus 6 is equal to our factor, which was x minus 1/2 times the quotient we have, which is 6x squared plus 22x plus 12. And now the strategy is to break down this part of the polynomial by going through and doing either factoring, quadratic formula. It doesn't matter. But the one thing you will notice right away is you can factor out a 2 from that entire polynomial. So we really have x minus 1/2, and then we've got a 2, and then we have to factor x squared. Sorry, it's a 3x squared. 6 divided by 2 is 3. 3x squared plus 11x plus 6. And now we have to factor this or use the quadratic formula. I'm going to use factoring by grouping. And we know that 6 times 3 is 18, and 2 times 9 make 18 and add up to 11. So this is really 2 times x minus 1/2. And then inside my parentheses, I've got 3x squared plus 9x plus 2x plus 6. And then I can factor this by grouping. So I've got a 2 and x minus 1/2. And then inside my parentheses, I can take out a common 3x, leaves me with x plus 3. Back there, I can take out a 2, leaves me with x plus 3. And so now when I factor this, I have my 2. I've got my x minus 1/2. I've got the x plus 3 I can take out, that's common. And then finally, I've got a 3x plus 2. And again, if I was to take and multiply all of this out, I would get back to the original polynomial f of x. And it's a nice way to check your work, but it is a lot of work to multiply all that out as well. All right, so now let's move on to the next problem. And I didn't factor that right. Oh, actually, we did. We did factor it completely. But in my notes I went over in class, I also went through and I listed out the zeros. It's not asked for in this problem, but let's just kind of write them off to the side for reference. We have 1/2. We've got -3, and we've got -2/3. And if you do factor this a little further, you could actually factor out a 3 from the last term. And when you do that, you'll get the truly factored form, which is going to be 6. I'll do this in a different color, though, so it doesn't look so hard to read. So again, this is going to be the 2 times the 3 I'm factoring out is a 6 times x minus 1/2 times x plus 3, and then back here x plus 2/3. Again, I just divided that last factor by 3 and then put the 3 multiplied with the 2 to get the coefficient of 6. And again, these two things here are exactly equal, these two expressions. So the last one is truly the factored form because of the fact that each of the factors leads with an x. But technically speaking, the one before it was also factored because it was a product of prime factors. So again, these are different ways to factor and break down this polynomial. And again, you should have 3 zeros because it is a cubic polynomial. All right, so let's move on to the next problem. And it's going to be more of the same. They're going to want us to go through and take zeros now and build the polynomial in reverse. In other words, here's the zeros, build a polynomial. Keep in mind the answers here are not going to be unique. There's multiple ways to write the answer, especially when you start having different coefficients in front being multiplied. So let's go through now and do this problem where we're building backwards. All right, so first thing you're going to notice here, they're telling us we're going to have a 5th degree polynomial for our final answer. The next thing you should notice here is that we have a multiplicity of 3 for one of the zeros. So let's go through now and write down a candidate for our polynomial. So let's go through and write down what happens when we have a factor x minus 2. Well, if you have an x minus 2, that means 2 is the 0. So my first factor is going to be x minus 2. And again, if you substitute in a 2, you will get 0 for an answer. The next one is going to be x minus 5 halves. Once again, if you were to substitute 5 halves into this expression, you get an answer of 0. And then finally, you have a 0 equal to the number 0. And I'm going to write it this way as x minus 0. And then I'm going to put a third power on it because it has a multiplicity 3, which means it's repeated 3 times. So that's going to be x cubed times the result of x minus 2 times x minus 5 halves. And we'll just multiply out the x minus 2 and x minus 5 halves. So I'm going to have an x squared minus 5 halves x minus 2x plus the number 5. And then if I combine like terms, if I have a negative 5 halves minus a 2, that's really the same thing as negative 4 halves. So that's minus a 9 halves x plus 5. And then if I multiply in my x cubed, I'm going to get x to the 5th minus 9 halves x to the 4th plus 5x to the 3rd power. And unfortunately, we can't keep the answer like that because we want to have integer coefficients in our polynomial. So I'm going to multiply this whole thing by 2 to clear that out. So my polynomial is going to be f of x is 2x to the 5th minus 9x to the 4th plus 10x to the 3rd. And this answer is not unique because any multiple of this polynomial will have the same zeros. So think of it as a candidate for an answer, but it's not the only answer. It's one of many. All right, now let's do the same thing for the next problem. This time around, you'll notice it has complex zeros or imaginary zeros. So when I write out my polynomial, I'm going to have x minus 1, because 1 is a 0. I'm going to have x minus 3i and x plus 3i. We now want to find the easiest way to multiply this out. And it's always better to multiply out the complex part first as conjugate pairs. So we're going to multiply this part first and then multiply that result by x minus 1. All right, so in multiplying that out, you still got the x minus 1 sitting in front. Inside the multiplication, we've got an x squared plus 3ix minus 3ix minus 9i squared. And if we think back to before, remember I squared is the same thing as negative 1 because I is just the square root of negative 1. I said negative 1, but I sure didn't write it. So this is the same thing as x minus 1 times x squared. Then you notice that the two middle terms cancel out. That will always happen when you have a complex conjugate pair. And back there, the minus 9i squared becomes a plus 9. And now we can multiply that out using FOIL. We get x cubed minus x squared plus 9 times x minus 9. So our polynomial, f of x, one of the possible answers, x to the third minus x to the second plus 9x minus 9. And if you were to do the process in reverse and find the 3 zeros for this function, you would get those 3 zeros back again. Remember again, this is not the unique answer. Any multiple of this polynomial will also satisfy the zeros condition that we have. So this is a possible answer, but not the only answer. All right, so for our next page, we're going to look at what's called the rational zeros theorem. And this is a good way to find the candidates for the zeros, but keep in mind that the answers that you get are not going to be all of the zeros. In other words, you're going to get a lot more answers here than the degree of your polynomial. And even though it's not really mentioned in the note quiz explicitly, the degree of the polynomial will tell you how many zeros you're going to have if you count multiplicities. So this polynomial here would have at most 6 different zeros, and you're going to see in a few minutes here that the possible zeros is way more than 6. So the idea here is this. You always take your polynomial that you're studying and you want to write it in descending order. And then you're going to have a highest power leading the way. The number in front of that is called the leading coefficient. At the very end of the problem, you are going to notice that you're going to have a constant number. It could possibly be 0 because you could be missing a constant term. That's fine. This theorem still applies. But anyways, that's called the constant coefficient. So again, the front is the leading coefficient in front of the highest power. The number by itself at the very end is the constant coefficient. So this theorem says that the possible zeros that are rational for this polynomial will be the factors of the constant coefficient divided by the factors of the leading coefficient. So what you want to do first is you want to write out the factors of the constant coefficient. So we'll do that in blue. It's always fun moving and erasing. All right, so here we go. So our constant coefficient in this case is equal to -6. And we're going to write out the factors of just 6. We don't have to worry about the sign in this part of it because that'll be accounted for in a few minutes. So again, constant coefficient is 6. Let's list out those factors. So 1 goes into 6, 2 goes into 6, 3 goes into 6, 4 does not, 5 does not, but obviously 6 does. So there's 4 divisors or factors of 6. Now we look at our leading coefficient. For this problem, it is 4. So 1 goes into 4, 2 goes into 4, 3 does not go into 4, and finally 4 goes into 4. So that's my possible factors for each. And now what you do is you take the numbers in the constant coefficient list and divide each of them by the numbers in the leading coefficient list, including the possibilities of pluses or minuses. So in other words, I'm going to have taking that first leading one from the constant coefficient, plus or minus 1 over 1. I now take that same 1 and put it over the 2. Then I take that next one and I put it over 4. I'm now done with the 1 in the top. I move on to the 2. I'm going to have plus or minus 2 over 1, plus or minus 2 over 2, and plus or minus 2 over 4. Moving on to the 3, plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 4, and then finally the 6, plus or minus 6 over 1, plus or minus 6 over 2, and plus or minus 6 over 4. Now, if you first glance at this list, it looks pretty long, but remember, we do have some duplicates here. For example, 1 divided by 1 and 2 divided by 2, they're exactly the same thing. So therefore, let's go through and just write down the unique answers that we have. The first one we get is plus or minus 1. The next one is plus or minus a half. The next one is plus or minus a fourth. And then we've got plus or minus 2. I'm going to strike out the 2 over 2 because 1 is already in the list. I'm going to also strike out the 2 over 4 because that simplifies down to a half. But the plus or minus 3 over 1, which is just 3, is already there. Is that now going to be in the list? 3 halves, unique, brand new. Plus or minus 3/4, brand new. Plus or minus 6 is brand new. And that's where I end because 6 divided by 2 is just 3, which is already in my list. And 6 over 4 is 3 halves. It's already in my list. So I get a total of, looks like 16 possibilities if I count the plus or minuses. 16 possible different rational zeros. But again, I have a 6th degree polynomial, so at most 6 of those will be zeros. And remember, we also have the possibility of having complex numbers for zeros with i's in them, and we also have the possibility of having radicals in there. This doesn't even mention those. This is all about just the ones that could be rational, written as nice, clean fractions of integers. All right, so let's move on to our next problem, and we're going to be using the strategy of finding possible zeros to figure out what to divide by to break it down. So in doing so, we're going to look at first mentioning the possible zeros. And again, those possible zeros are going to be the factors of the constant coefficient 8 divided by factors of the leading coefficient, which in this case is 1. So it's going to be 1, 2, 4, and 8 divided by 1. So that's really going to be plus or minus 1, plus or minus 2, plus or minus 4, and plus and minus 8. So we've got 8 different options for rational zeros. In the interest of time, in the interest of looking at the problem, it turns out that -1 is one of those zeros. You can sometimes see this by just looking at the numbers in the problem and imagining yourself substituting in either a 1 or a -1 or a 2 and seeing if you get 0 for an answer. It's not cheating because you're using the fact that the value of the function gives you the value of the remainder. But again, -1 is our first one to try. So I'm going to take a -1, and again, this is just going off of a hunch. 1, -3, 4, and 8. Bringing down the 1 and multiplying, -1 times 1 is -1. Adding up a -3 and a -1, -4. -1 times -4 is +4. 4 plus 4 is 8. 8 times -1 is -8, and haha, 0. So -1 is definitely one of our zeros. And what that means is that so far, I know that my x cubed minus 3x squared plus 4x plus 8 is equal to x plus 1 times x squared minus 4x plus 8. So again, the idea is I took my 3rd degree polynomial and I rewrote it as the product of the divisor, x plus 1, and a quotient left over. Now we're going to go in and break this apart. You will notice that it sadly doesn't factor, so instead we have to use some algebra from before. I'm going to take that x squared minus 4x plus 8 and set it equal to 0. And then I'm going to use completing the square because I have a nice even b number. So I've got x squared minus 4x, leave some room, equals -8. Half of -4 is -2. -2 squared is 4. So I'm adding 4 onto both sides. Factoring the left, that is x minus 2 squared, and negative 8 plus 4 is negative 4. I can now take the square root of both sides. That gives me x minus 2 equals plus or minus 2i. Adding the 2 and putting it in front, I get x is equal to 2 plus or minus 2i. So my zeros are going to be negative 1, which we found by guessing and dividing, 2 plus 2i, and 2 minus 2i. And again, you will notice that these two complex numbers are conjugate pairs. They form a conjugate pair of numbers. Now, when I write my polynomial in factored form, it's going to look a little ugly. But my g of x is going to have the first factor of x plus 1. It's always x minus the 0. And then I'm going to have x minus 2 plus 2i, and an x minus 2 minus 2i. And that is the completely factored version of that polynomial. And again, to reiterate, if I multiply all of that out carefully, combine like terms, it'd take me back to the expanded form of g of x. All right, so again, the goal here is to break apart these polynomials the best that we can. So for our next problem, we're going to attack a 4th degree polynomial and break it down completely. All right, so for this problem here, we're going to first start off by listing the possible zeros. And again, when we find those, we're looking at factors. So it's going to be the factors of the constant number, which is 24, divided by the factors of the leading, which is 2. So that's going to give me a lot of possibilities if you think about 24. We got a 1, a 2, a 3, a 4, a 6, an 8, a 12, and a 24. There's a lot of numbers that divide into 24 evenly. However, thank goodness, the factors of 2 are just 1 and 2. All right, so now we're going to kind of go through and list out the possibilities using our plus or minuses. So we've got plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 4 over 1, plus or minus 6 over 1, plus or minus 8 over 1, plus or minus 12 over 1, and plus or minus 24. That just takes care of the first row of numbers over 1. Good news is, when we start writing the fractions for 2, there's not too many. We're going to have plus or minus 1 over 2. 2 over 2 is already on there. It's a 1. We got plus or minus 3 over 2. We don't write 4 over 2 because that's equal to 2. Plus or minus, let's see here. We're going to have 8 over 2. Well, 4 is on the list. And see what is else left there. So let's see here. We got 3 over 2 is already there. 4 over 2 is 2. Nope. 6 over 2 is 3. Nope. 8 over 2 is 4. 12 over 2 is 6. And 24 over 2 is 12. So my list ends right there for possibilities. All right. So next up, again, this is the hardest part. In theory, you could potentially be dividing every single one of those numbers into the polynomial and crossing your fingers for a remainder of 0. But in the interest of time and not wanting to spend the next hour dividing, I'm going to take a hunch, which is 2. 2 does go in. Again, what a lot of people do in modern times now is to kind of go through with a graphing calculator and graph it and see the intercept as a 2. Or you could go to Desmos and graph it and see that it crosses at 2 as well. So 2 is a 0 because I'm going from a graph of this function. And I'm going to write down my coefficients. So 2, negative 7, 14, negative 28, and 24. But again, this division process can get very long if you don't have any hunches what your zeros are. So now let's do our division. I'm going to bring down the 2. multiply and get 4, add up and get negative 3, multiply to get negative 6, add to get 8, multiply to get 16, add to get negative 12, and 2 times negative 12 is negative 24 for that highly precious remainder 0. So far we have seen that 2x to the 4th minus 7x cubed plus 14x squared minus 28x plus 24 is equal to x minus 2 times my quotient. Remember, I count down. 2x cubed minus 3x squared plus 8x minus 12. And I didn't realize this before, but this could actually be factored by grouping. But let's not do that. Let's just kind of, again, go to a graph or look at it from maybe Desmos. So from a graph, you will see that it crosses at the number 3 halves. So 3 halves is another 0. It would have been the same result of just going through and factoring by grouping. So when I go ahead and do my division, again, don't go back to the original polynomial. You want to go to the simplified one you just got from dividing. So I want my 2, my negative 3, my 8, and my minus 12. Bringing down the 2, 3 halves times 2 is just 3, negative 3 plus 3 is 0, 3 halves times 0 is 0, 8 plus 0 is 8, 3 halves of 8 is 12. And again, just think of it as 24 divided by 2. Remainder is 0. So now I know that 2x to the 4th minus 7x cubed plus 14x squared minus 28x plus 24 is equal to an x minus 2 times an x minus 3 halves times a 2x squared plus 8. And now I can take that little tiny leftover, 2x squared plus 8, and set it equal to 0. And in doing so, I get 2x squared equals negative 8. Divide both sides by 2. And I get x squared is negative 4. Square rooting. I get x is equal to plus or minus 2i, a conjugate pair. So now I've got my zeros. I know that 2 is a 0, 3 halves is a 0, and so is plus or minus 2i, and I'm done because I found 4 zeros for a 4th degree polynomial. So now let's write our answers very carefully. First, when I list out the zeros, again, 2, 3 halves, 2i, and negative 2i. When I write my factored polynomial, I have to be very careful because I divided out a 2 along the way. I did it right here at this step. So I have to make sure I account for that. So I have to multiply my answer by a 2 to balance it out. And then I've got my x minus 2, got my x minus 3 halves, my x minus 2i, and then x plus 2i when I do the minus negative 2i. And again, I could multiply all of this out and come back to the original polynomial. I also will make a little note here. You can kind of think of this too, in that 3 halves there, as multiplying and canceling out the fractions so that I get integer coefficients. All of your quotients of your fraction zeros have to be represented by a leading coefficient out front to make sure that we get back to the original polynomial. So just something to kind of keep in mind here as you go. Opposites. All right, so now let's talk about what's called the conjugate zero theorem. And it says something that's pretty simple to understand. If you have a complex number given to you as a 0, its conjugate must also be a 0. So Remember, when you find a conjugate, you're just changing the sign between the real part and the imaginary part. So for this problem here in particular, we're going to go through and try to break down this polynomial. And if you were to graph it on a calculator or in decimals, you will see that there's no real zeros, but there are 4 zeros because it's a 4th degree polynomial. So we're going to show you how to actually find all the zeros given this complex zero. There's 2 ways to go with it. You could, in theory, use synthetic division with 1 minus I and get a remainder of 0, and then use the conjugate to divide that answer and knock it down to a remainder of 0, and you're left with an x squared polynomial, which is quadratic. So that would work in theory. However, that is a very messy and tedious way to do it. Instead, what we're going to do is the following. We know that x is equal to 1 minus I is a 0. It's given to us. But so is x equals 1 plus I, because that's just the conjugate. So that's actually 2 of the 4 zeros right there. So this is the part that gets kind of clever. If you know that x equals 1 minus I, you can subtract 1 from both sides and get x minus 1 equals negative I. You can then square both sides of this. And when you do that, you're going to get x minus 1 twice equals negative I squared, which is going to be really I squared, because when you square the negative, it cancels. Multiplying this out, you get x squared minus 2x plus 1, and I squared, remember, is negative 1. So this turns into x squared minus 2x plus 2. And so therefore, if these are both factors of the polynomial, dividing it in must give you a remainder of 0. In other words, I can take my x squared minus 2x plus 2 and divide that by long division into x to the 4th plus a 2x cubed plus a 7x squared minus 18x plus 26. And again, as I said earlier in the video, you can't use synthetic division for higher power division because of the fact that it only works for first powers. So now you ask yourself, x squared times what makes x to the 4th? That is x squared. We now take that x squared and multiply it through the 3 terms in the front. That gives us x to the 4th minus 2x cubed plus 2x squared. Then remember, we change our signs. So we're going to have a negative here, a plus there, and that's going to be a minus back here. And then remember, we're adding up after we change the signs. So we're going to get a 4x cubed plus a 5x squared, and now is a good time to bring down that minus 18x. Repeat the process. X squared times what makes 4x cubed? It's got to have a 4 and it's got to have an x. So that's going to be plus 4x. I now multiply. I got a 4x cubed minus, and I did not bring down my square, did I? That is a 5x squared. All right, so let's go back. 4x cubed and then minus 8x squared. And then plus 8x. Just like before, I changed my signs. So that's a negative and a plus. And that is a minus. I said a minus. There we go. Adding up like terms, I'm going to get a 13x squared. And then I'm going to have a minus 26x. And I bring down my final plus 26. And then I ask myself, well, what would I multiply an x squared by to get 13x squared? The answer is 13. So I've got a 13x squared minus 26x. Can't believe I forgot that again. And then plus 26. Change the signs and add them up. Well, would you look at that? You're going to get exact, a page, didn't I? You're going to get exact opposites. Let me erase that. Forward over, there we go. So changing that last sign, if it will let me. Will it let me? Yeah, there we go. That is a minus. So adding those up, remainder is 0. So now, off to the side, I have to figure out the zeros of x to the 4th plus 4x plus 13. And I can complete the square again. And that's next squared. I don't know where the 4 came from. Frazzled with technology. That's what we'll say. So we've got an x squared plus a 4x. Leave some room. Equals negative 13. Again, I'm going to add 4 to complete the square. Half of 4 is 2. 2 squared is 4. So I'm going to add 4 to both sides. And I get this time x plus 2 squared is equal to negative 9. Just like before, square root. I get x plus 2 equals plus or minus 3i. So x is negative 2 plus or minus 3i. So I now have my 4 complex zeros. My complex zeros are 1 plus or minus I, and I've got negative 2 plus or minus 3i. When I write this in factored form, it's going to look pretty hideous, but here we go. My polynomial, when it's all said and done, is f of x is equal to x minus 1 plus I, x minus 1 minus I. I'm going to have an x minus negative 2 plus 3i. And then finally, x minus negative 2 minus 3i. Close up those parentheses and fix that x. So now when I look at this right here, I could, in theory, multiply all this out and get back to the original polynomial. But again, you will notice here that those 4 zeros is going to be represented there in my factored form as x minus the 0. And if I was to multiply all of that out, I would get all the way back to the original polynomial, which is pretty nice, but also kind of messy. All right, let's move on to our very last problem. In our very last problem, it is a building backwards problem where I want to go in and build a polynomial from given zeros. This time around, I have an extra requirement. I want f of 0 to equal negative 32. So that will remove that infinite possibilities we talked about earlier with multiple answers and just give us one definitive answer. All right, so let's go through and write our down payment on our function. We know that f of x is going to have a constant in front of it so that I can get negative 32 out when I plug in 0. So I'm going to call that constant a. It's customary to do so. And then because 4/5 is a 0 with multiplicity 2, x minus 4/5 squared has got to be the first part of my factorization. And they also tell us that x equals negative 2/3 is a 0. So x plus 2/3 must be a factor. And so again, we've got our multiplicity 2 for the 4/5, and we got a multiplicity 1 for the negative 2/3. And then we need to multiply all this out. And it doesn't really matter how we multiply it, but a lot of people will probably multiply the x minus 4/5 first. So let's do that. And because we've got some messy fractions to work with, we'll kind of slow down and show all of those messy details. And don't forget there's an a in front of this. I almost left it off by accident. All right, so when I do my FOIL, x times x makes x squared. 4/5 times x just shows up twice. And then 4/5 times 4/5 makes 16/25. And that's still multiplied with my x plus 2/3 hanging out behind there. All right, next up, we will combine like terms. So that's a times x squared. And 4/5 and 4/5 makes 8/5. And now I'm going to go through and distribute very carefully that x is going to hit all three of those terms. So I get an x cubed minus 8/5 x squared plus 16/25 times x. And then the 2/3 is going to hit everything. So I get a 2/3 x squared. And then I'm going to get 2/3 times 8/5. And that is going to make, I can do that. That's 16/15. Yeah, so that's minus 16/15x. And then finally, I'm going to take 16/25 and multiply that by 2/3. That's going to make 32/75. The last thing to do in this part is to combine our like terms together. So that is a times x cubed. Combining my x squareds, I'm going to get 14/15. You may need to get a common denominator to add those up. For the 16/25 and the minus 16/15, they're going to make a minus 32/75 times x. Again, just adding fractions. And then I've got a plus 32/75. So that is my expanded part. But now I have to make sure that when I find f of 0, I get 32, but negative. So f of 0 has got to be negative 32. And now if I substitute 0 in, I still have an a out front. And those first three terms, 0 cubed minus 14/15, 0 squared, minus 32/75 times 0, plus 32/75 is going to give me the first terms just drop out because that's 0, 0, and 0. So I end up with this little miniature equation of negative 32 equals a times 32/75. To solve it, multiply both sides by 75/32. And that's a 7. Getting kind of sloppy looking there. There we go. And in this case, on the left side, the 32's cancel out. And it leaves me with a is equal to negative 75. So my polynomial is f of x is equal to negative 75, which we just found, times x to the third power minus 14/15 x squared minus 32/75x plus 32/75. And again, remember, we can't leave our answer with fraction coefficients. So we got to multiply that 75 into all four of those numbers there. And in doing so, we get our final answer. F of x is negative 75 x cubed. And then the middle number is going to be a 70 because 15 goes into 75 evenly. And it's going to give us a 70. And then we're going to have a 32x. Oh, and it was negative 75. So watch those signs. I almost made a mistake. That's going to be a plus 32x minus a 32 at the end. And again, to reiterate, you could find the 3 zeros of this polynomial. You get 4/5, 4/5, and negative 2/3. And then if you substitute in 0 for x, you will get out a negative 32 for an answer. So we are looking good. And that is the end of note quiz number 9. A lot of work. And again, you are welcome to kind of go through and practice these problems. And if you have questions, please reach out for help.